Good day, Doctor. We are from Group 1. In this video, we are going to present our VLSI project with the title of Synopsys 3-bit digital synchronous counter. My name is CHUN and my team members are CHONG and Nabihah. So for introduction, in digital electronics, a counter is a sequential circuit that outputs a predetermined sequence of binary numbers in response to a clock pulse. Synchronous counter is a counter where all the flip-flops are triggered with same clock signal simultaneously. In this project, a 3-bit digital synchronous counter in counter sequence of 0 to 2 to 4 to 6 and to 0 was designed using the flip-flop. At the same time, the corresponding Verilog code was written using Verilog HDL language and simulated and synthesized using Synopsys EDA tool. Next, for the methodology, at the first we will draw the stage diagram, derive the truth table, and also draw the sequential circuit of the counter based on the counter sequence given. And then next, we will using the Verilog HDL to write the codes for the counter, and then using Synopsys VCS to simulate the design and also get the waveform result. And we will compare the waveform result with our truth table. And next, we will proceed to the synthesis step. So in this step, the codes will be converted into the logic combination gate, and a gate level of netlist will be generated. And next, we will proceed to the timing analysis, where the timing, area, cell, and clock report will be obtained. And then next, we compare the report result with the timing requirement. If the timing requirement is met, then it means that our design is correct. So that's all for methodology.
So for the Verilog code, we will save in the counter 3-bit, and the test brand for the counter will be the TB_3-bit counter. So now we can get into edit the Verilog code of the counter. First of all, I will briefing to explain the code. So our input will be W, clock, and reset. The W will be representing to the enable, and we have the output F, and will be a 3-bit output. So our step will be a 0, 2, 4, 6, and repeat to 0. So, and this column is for the reset. So once it's reset, the next step will be the first step, which is the 0, 0, 0. So next, if the present set is 0, 0, 0, and next step will be 2, which is B. And move on to B. Present set is B, which is 2, and the next step will be 4, which is C. So for the continuous code will be the same logic, and once it reset, it will move back to the A, which is the first state, 0, 0, 0. Next, we can get into our test plan code. So here will be our test plan code. So the same will be 3 input and 1 output, and this will connect to the counter code. So that's all for the Verilog code.
Need to click this button. So now here is the waveform result that we obtained, and then we zone full. So now here, as you can see, when the reset is 1 and the W, which is representing to the enable, is 0, then the output will be 0. However, when W is 1 and then the reset is 0, then the output will become like the counter sequence that given, which is from 0 to 2 to 4 to 6 to 0, and then it will keep repeat until the period that we set in test bench, which is 400 ns. And from the waveform that we've obtained, and by comparing it to the truth table that we have done, it shows that both results are the same, and it indicates that our design is correct. So that's all for me, and I will pass to my team member to continue the next presentation. Thank you.
Magnetic wheel. So this is our block diagram, and I insert and double click it to see the detailed design of the block diagram. After that, I need to design the design constraint with this add specification by using this code. After I insert the design constraint with this value, then I can continue with the design, compile design, okay, and also get the new logical record view. schematic view. And the block diagram, the circle inside will change like this. So I will continue with the report for the area report, also the cell report, and also the clock report and timing report in the PPT slide later. Okay, so I will continue to the area report. So our design synthesis feature create using SAD 90 nanometer max VG library for nanometer process, and also 7 cells with 6 port 10x content of 4 combinational and 2 sequential. And for the area analysis, our design total cell area is 103.13 units and total area is 104.5 units. It is reasonable area efficiency with non-combinational components dominating. And also for the design assessment, our design is well structured and appropriate size for a 90 nanometer process. Next, for the timing report, we have the positive slack significant. There is 2.64 unit slack allowed for optimization or additional functionality. And for the evaluation details, our design is sufficient margin for setup time constraint. Our overall timing characteristics are acceptable for 90 nanometer process technology. Next, for the cell report, it identifies 6 cells totaling 103.13 units, and the not-able cell U3 inverter, U5, U6, XNOR and XOR gate, U7 is a NAND gate, and the dominant contribution from 2 non-combinational flip-flop stack register 0 and stack register 1. And for the clock report, the clock signal has 5 nanosecond period oscillating between 0 to and 2.5 nanosecond, and the clock skew detail both rise and fall delay for clock signal are 0.5 nanometer, indicating the symmetric behavior based on our specification. And our minimal skew contribute to a stable and reliable clocking design. So that's all for me. Thank you.
Lastly, for the conclusion, our project centers on the designing and analyzing the 3-bit synchronous counter from 0 to 46 and back to 0 using the Synopsys EDA tool. Employing a symmetric approach, we drive the key artifacts like the state diagram and the schematic security, and the use of D flip-flop and the Verilog HDL facilitated the efficient representation of the simulation and ensuring the counter's functionality. The synthesis with the Synopsys design compiler produced a well-structured design meeting the constraints evident in the report. The simulation validates the accuracy of the counting sequence. So in summary, our project successfully implements a 3-bit synchronous counter, showcasing efficiency, robustness through a careful design, simulation, and synthesis project. Last but not least, we have signed that have 10 references in our report. That's all from our group. Thank you.